Hello and welcome to LittleBIGPhysics, a series in which we try to figure out the mechanics of the world of LittleBIGPlanet from the ground up. Last time, we took a break from all the fancy theory to go back to the first concept we explored, length, and measure how big levels and their grids are. Today, I want to take a closer look at the second concept we explored, weight, a little more deeply. It's no secret that some materials in LittleBIGPlanet are heavier than others. We've discovered that heaviness can be measured, and that doubling the size or amount of something doubles its weight, but that doesn't tell us everything. Blocks of the same size, made of metal and wood, don't weigh the same, for instance. Is there a way that we can quantify how heavy one material is compared to another? Let's think about this a bit before we get to testing anything. It turns out that a minor detail that I mentioned is actually very important. Doubling the size or amount of something doubles its weight. What I mean by this is that the weight of an object doesn't depend on its shape, location, or anything like that. All that matters is how much you have of that material, not whether it's in one piece or many, or anything else. We call this a linear relationship. If you graph the total weight against the amount of material, it makes a straight line. You might also call it proportional, since if you have zero amount of a material, it has zero weight too. Why do I bring this up? Well, there are two ways to reach the conclusion that I'm getting at. One is that if we look at the units we've defined so far, it turns out we already have units for distance and heaviness, and we can use those units of distance to determine how much we have of a material. If we have a square block that's 2 lengths tall and 2 lengths wide, for instance, we can multiply its height and width to find its area, 4 square lengths. Finding the area of any other shape will be a bit harder, but it can still be done, or at least approximate it pretty well. We can use this area as a measure of the amount of material that we have. Thus, since each material has its own weight per amount of that material, or area, we can express the heaviness of that material as a number, in masses per square length. Alternatively, if we look at that graph we made earlier, we can notice that it's steeper for heavier materials and less steep for lighter materials. If we measure the amount in square lengths again, then the slope of the line is actually the number we just described, a ratio in masses per square length. There's just one small complication. Objects in LittleBIGPlanet don't just have 2 dimensions. They aren't just however tall and however wide, but they also have thickness. They could be 1 layer thick, 2 layers thick, 3 layers thick, or even more notably, they can have another special thickness, the thin thickness, where they're on layers separate from the thick layers, called thin layers. How do we account for that? First, we need to determine the relationship between thickness and heaviness. Let's go back to the scale we made in the second episode. If we put a block of whatever size on the scale, it gives us a measurement in masses. But what happens if we change the block's thickness? Intuitively enough, doubling the block's thickness doubles its weight. The same happens when we triple the thickness from 1 layer to 3 layers thick. When we change from a single thick layer to a thin layer though, the weight is right about 1/5 of the thick block. Now that we know how heaviness varies with thickness, we have everything we need to describe the heaviness of a material. A material has a heaviness for a given size and thickness, meaning we can describe that heaviness in terms of weight per size and thickness. For a block in the thick layers, we'll describe it in masses per square lengths thick for thick layer, while for a block in the thin layers, we can instead use masses per square length thin for thin layer. We'll consider these our units of density, or a measurement of how heavy an object of a given size and material is. For example, a block occupying 2 thick layers with a size of 4 square lengths and a density of 5 masses per square length thick will weigh 40 masses. For a block in a thin layer, we can just divide the thick density by 5 to get the thin density and work from there. If the block that we just had was in a thin layer, it would instead weigh 4 masses. Now that we know how to describe density, we can measure it for different materials. I admit that I haven't tested every material, there are lots of them, but some preliminary testing shows that the density doesn't depend on the material itself, but the type of the material. For example, all wood seems to have the same density. The only exception I've found is tin foil, which weighs as much as metal despite being listed as a type of cardboard. Here are the densities that I've found. Do you notice anything strange here? There are 2 things that stand out to me. One is that there are actually a lot of repeated values. This is a little bit more apparent if you rearrange the list in order of increasing density. Take a look. In fact, aside from the sponge material, we only have 3 different densities across all 8 materials. On top of that, sponge is the only material on this list to have a unique density. There's something else that I found even more interesting though. Do all these numbers look a bit similar to you? Let's multiply them all by 3. Hold on just a moment longer though. Multiplying the densities by 3 is the same as measuring the density in terms of maximum thickness, which is 3 thick layers. Thus, we can actually express these measurements in units that I'll call masses per square lengths m thick, where m thick refers to maximum thickness, 3 thick layers. This is the very definition of a beautiful coincidence. At maximum thickness, the density of each material is actually a clean number. Thus, for the sake of simplicity, I'll keep track of these numbers in masses per square lengths m thick, so that they're easier to read, and we can just cut that into 1 or 2/3 for blocks 1 and 2 layers thick respectively. Since blocks in thin layers weigh 1/5 that of blocks occupying 1 thick layer, and blocks occupying 1 thick layer weigh 1/3 that of a block occupying all 3 thick layers, density in the thin layers is 1/15 that of all 3 thick layers. With that, we can now predict the weight of any material, so long as we know its size and thickness. I hope those of you watching enjoyed this episode half as much as I did. Those moments where everything falls into place, where a funny little coincidence turns into a new discovery, are my favorite throughout this entire experience. They don't come easily either. I thought that all the 3s and 6s were an interesting chance happening when I first took the measurements, but I didn't realize that using maximum thickness would give such clean numbers until I was actually writing the script for this episode. I can only hope that we'll make such discoveries again as we move forward, but it'll no doubt take some work to get there. In any case, until next time, stay curious.